This next question asks us to write the 5 congruence conditions that we covered in this chapter, and then identify which one you would use to prove that the triangles at right are indeed congruent to each other. So there's just 5. All of them have sides in one way or another. The 5 congruence conditions, I guess not written in any particular, I think this is the order they are on the whiteboard in the classroom, is angle, side, angle. So 2 pairs of congruent angles in each triangle and connected by a congruent side. Also an angle, and then a congruent side, the non-included side. Also, all 3 sides in one triangle are congruent to all 3 sides in another. Side, side, side is a congruence condition. Also, side, angle, side is a congruence condition. And then the 5th one applies only to right triangles. So you need to have right-angled triangles. They would have to have a congruent hypotenuse, right? The fact that there's a hypotenuse there kind of tells you that it has to be a right triangle, right? Because only right triangles have a hypotenuse. This is the hypotenuse of this right triangle, the green segment. And they also have to have a congruent leg. So one of their corresponding legs is congruent and the hypotenuse is congruent. That would force those triangles to be congruent by HL, or hypotenuse leg. Now if you look at the diagram over here, it asks us to decide if these triangles are congruent, and which congruence condition would be used to show that they're congruent. So one of the things we see right off the bat is they do give us a clear pair of congruent angles, right? So we've got a pair of congruent angles. The other thing that we also know is that they share the side FH. Those are congruent. Now if you look at these arrows are indicating that these 2 line segments, and let me write them down, it's segment GH, and they're parallel to each other. GH and FE, I could say, are parallel to each other. And because those are parallel lines and they're cut by this transversal, I'm just going to make it a little bit longer, right? So there's this transversal that goes through them. It turns out that this angle, right, and this angle have to be congruent because those are alternate interior angles. So whenever 2 parallel lines are cut by a transversal, we get a pair of alternate interior angles that are congruent to each other. And again, that's a great thing to kind of throw into GeoGebra and take a look at and experiment with. Well, looking at this diagram, then you can see, if I look at my red angles, right, I've got these angles in red, and then I have the side in blue that connects them, and then I've got these angles in green. And notice the order of the triangles, right? It's triangle F to H to G. So F, H, G. That's the green, then the red, and then this other angle. And that goes with triangle H to F to G. Right, so they're following exactly the same order there, and it feels like they're kind of flipped, but we've got to make sure we're matching things up correctly. So this is the correct order if you look at the congruence statement down below. Triangle FHG, that's the top one, is congruent to HFE, and notice the order flip there. And those are congruent to each other by the angle, side, angle congruence condition. Next question, I think this is the last one on this page then too. It says, find the next 3 values for the sequence below, create a table of values, a graph, and find the equation for this sequence. Well, if I look at the first few terms, right, from 9 to 27, from 27 to 81, it becomes pretty evident that what's happening is as I jump forward, I'm multiplying times 3 each time. So we're just going to keep that going, times 3. If I take 81 and I triple it, I get 243. If I triple that, I get 729. And 3 times 729 is 2,187. So, you know, this is my first term, my second term, my third term, my fourth term, my fifth term, my first, second, third, fourth, fifth, and sixth term in that sequence. So I have 6 terms there. 1, 2, 3, 4, 5, 6. Okay, so I could create a table to just basically record the same information. So I could say I've got my term number, and term number 1 has a value of 9, term 2 has a value of 27, term 3 has a value of 81, term 4 has a value of 243. Term 5 has a value of 729. And then finally the last term, the sixth term, right? 1, 2, 3, 4. The sixth term has a value of 2,187. Now we're asked to plot those values as well. So this is a sequence. So remember, sequences are discrete creatures. We can't talk about the 5.2 term or the 5.5 term. My domain is restricted to just the integer starting at +1 and moving forward from there. So if you're looking at your table of values, when the first term had a value of 9, which should be just somewhere right here, right just below the 10. The second term had a value of 27, so here's 30, so somewhere in here is 27. And then the third term jumps all the way up to 81, so way up here at 81. So I would like to include the 0th term, but except that's not part of our sequence. And I'd like to connect it because I'd get more of a feel for what's going on. So, you could connect it. Just in general, we wouldn't really connect these because it's a sequence and the things in between don't make sense. But it's nice to kind of look at that. You can see the pattern if they are connected. And then finally, the equation for this. So we talked about this in class while several of you are working on it. We're using repeated multiplication, and our tool for showing repeated multiplication is exponentiation. That allows us to show that we're multiplying by the same value again and again and again. We also need to know our 0th term. So if I want to write the equation for this term, in general it's y equals a times b raised to the x power. A has to be the 0th term, 0 term, which we don't know, and b is my multiplier. So, and I know that that's 3. I continue to multiply by 3. Well, if my first term is 9 and I'm multiplying by 3 to move forward, I could divide by 3 to get my 0th term. 9 divided by 3 is 3. So my 0 term for this sequence is 3. So I would write y equals 3. And my multiplier is 3, and then raised to the x power. So please spend some time thinking about what this says, right? The first term is 3 times 3, because that's 3 to the first. The term after that is 3 times 3 times 3. Notice there's 2 3's because it's 3 squared. And I've got 3 times 3 times 3 times 3, because that's 3 to the third. And then the fourth term is 3 times 3 times 3 times 3 times 3. There's 4 of those, right? So repeated multiplication is shown with exponentiation. Repeated addition, we show that with multiplication, right? If you're adding the same thing over and over and over again, multiplication is the shortcut notation for that. So that's pretty much all of the parts for question 5.